Welcome to a brief description of rational functions. A rational function is a ratio of two polynomial functions. Notice the word ratio in the title. It's not rational as the opposite of irrational, it's rational as a ratio. Here we have a polynomial over a polynomial, polynomial over a polynomial, polynomial over a polynomial. The first thing you'll be asked to figure out is the domains. And what you will do is set the denominator equal to 0. Yes? So in this case, obviously, for f of x, x cannot equal -3, because that would zero out the denominator. The others you're actually going to have to factor. So g of x would be equal to, let's see, x minus 3 times the quantity x plus 1. And h of x's denominator factored would be x plus 2 times x minus 2, difference of two squares. So here, x could not be equal to 3 or -1. And here, x could not be equal to plus or minus 2. Yes? Good. Now, as far as, so this gives me the set of numbers that are not in the domain. One of two things is true. They are either a whole or it is a vertical asymptote. In order to do that, we have to factor both the top and bottom. F of x obviously is, when we look for a whole, basically if I took a function 1 over x plus 1 and multiplied it by, say, x minus 1 over x minus 1, yes, I would have a function that looked exactly like this with a whole at 1. And that would look graphically, that looks like that. You know, there might even be a, let me see if I can get these up on the other. Okay, so let's take a look here. I believe these are our functions. We'll have to factor top and bottom. In the first case, the top and the bottom don't share a factor. There are no holes. In the second case, we're going to have to factor. We already factored the bottom, and so g of x would look like this. X minus 3 over x minus 3 x plus 1. And you can see basically that x minus 3 is on top and on the bottom, so there'd be a hole at x equals 3. Correct? So when x equals 3, there's a hole. Let's take a look at what that might look like graphically. Which one are we investigating? Oh, by the way, when you input these into the calculator, always include, look, parentheses around the top, parentheses around the bottom. Even when I enter just a 5x, I use parentheses every time. Otherwise, you're going to have a problem. Let's turn that off, turn that one on. All right, so here's our function. One thing you need to know is many calculators will draw a line right here along the vertical asymptote. That line does not exist. It's basically connecting negative infinity and positive infinity. But here's something interesting. We identified a hole at 3. So you can see that the graph doesn't show anything, but if I go to the table and I look at 3, you can see does not exist. It doesn't exist at 3. There's just a hole. There's not an asymptote which shows infinity, but there's a hole which says it does not exist. So that's the definition of a hole. Real quickly, on the third one, I would have to factor the top. All right, so listen, shortcut to factoring. I have to figure out what the zeros there are. I could factor it, I could use the quadratic equation, or I could simply go enter it right there and then use the power of the grapher to find the zeros. Snap to intersections root, -1/2 and 1. Okay? So if I was going to factor that, that would mean -1/2 would be 2x plus 1, right? Because the 0 would be, because the 0 would be -1/2. And then the other one was 1, so that would be x minus 1 all over x plus 2, x minus 2. So there are no holes in the third. Stay tuned for part 2.